All right. So we finished flexural design finally. I know that takes up a lot of the semester, but the rest of it is fairly simple stuff. So we're moving into shear. And first we're going to talk about the stress strain part of shear. And Justin, you're asking me about Moore circle. It's going to rear its little head right here for a hot second. But so here we have a beam, right? Like a 3-point bending beam. And I'm going to look at two little squares. Let me see if I can. One in the top and one in the bottom. And we have shear acting on it, on both. Shear stresses acting on these little elements. Right? Tau is for shear, right? And then in the top, where this looks like it's positive bending, so we've got compressive normal stress in the top. And compressive tensile, or I'm sorry, and tensile normal stress in the bottom element. So these are my stresses acting on these little elements. And if I rotate my elements 45 degrees, clockwise on the top one and counterclockwise on the bottom. If you've been studying Moore circle at all, you know, everything translates from having both. There's pure shear. When you rotate it 45 degrees, everything translates into either pure shear or pure normal stress, whichever way you go. So all of my shear stress is going to translate into increasing my compressive normal stress and a little bit of tensile stress.
See that?
On the top. So I don't have any shear, it's just pure normal stresses. These are the principal stresses. And I have the opposite situation on the bottom. I'm going to have large principal tensile stresses and small compressive stresses. I don't know how much you guys did this in mechanics, but it's basically like you draw, any state of stress, if it has like normal and shear stresses, you can rotate the element so that all of the stresses are normal, or you're at your maximum shear, just depending on how you rotate your element, the stresses change their directions. Well, the faces on which they act change directions. So in our top element, we have large inclined compressive stresses. And on the bottom, we have large inclined tensile stresses. This might start to give you a clue about shear, because concrete isn't very good in tension, right? So what if I'm talking about a large inclined tensile stress, that's going to result in a large inclined tensile crack. And that's the way that concrete fails in shear, is on an incline. So
since the load's coming down on the left, why wouldn't the top one be in tension, not in compression? Because if I'm imagining that beam bend down, the top is stretching and the bottom is compressing in my mind.
if we're talking about bending, right? We're looking, this picture right here is basically that half of the beam.
Gotcha.
Yeah. So we're in, right, this is in compression, and or in the bottom is in tension, bottom, top's in compression.
Gotcha. Yeah. Sorry.
That's okay. Always ask a question.
I might have a few questions since I've been trying to catch up.
Okay. So, this is also talking about the shear stress distribution across a cross section. I don't know if you guys talked about shear flow or anything in mechanics, but if this is my rectangular beam, The shear stress is distributed um, kind of parabolically, and the peak is at the center. You have your highest shear stress in the center. And it has a value of 2/3 times your shear stress over your area, right? Of your shear force, sorry, over your area. And if you're using the book, I have a note here that this tau might be like a little cursive B or a new, I don't know. But all this just to remind us that the distribution is not uniform. Luckily, we're generally talking about a rectangular section, not like in steel. Remember, the only thing that was carrying our shear was, because we're usually talking about a wide flange beam, and the only thing we took into account for shear was just the area of the web. Here, we're talking about something that's probably going to be a rectangle. Okay. So this is talking about the cracking behavior. I just alluded to it earlier. This is a figure that says the principal compressive stress trajectories of an uncracked beam. These trajectories, can't even say a word. They are the surface on which the principal stresses act. Meaning if we're looking at like this trajectory right here, the tensile stress is acting perpendicular to that. It's the surface. And these stresses, right, reach the tensile strength of concrete. And there's that cracking. this is a picture of cracks in a reinforced concrete beam. Again, we have kind of like a 3-point bend specimen. Although it's way out there. But if you guys remember your shear and moment diagrams, yes, they're coming back. Right, for like if you have like a single point concentrated load on like a simply supported beam, well, actually, well, I was going to draw it, but I was going to draw it incorrectly. Right, your shear is that. If it's a distributed load, your shear, right, just like that. You know, your moment, right, for a single concentrated load, for a distributed load. So what do you notice at the center? Your shear is usually a minimum and your moment is the maximum, right? So if we're looking at these cracks right here at the center, these are all flexural cracks. See how they're basically vertical because you have your pure tension on your section, right? You generally have a high moment, lower shear at your center. When you get out, further out, this is where you have the incline crack. Because now you've got shear and moment. And that shear is inclining your failure surface. Okay? That's why it looks the way it does. Now we're going to pull out our mechanics and materials graph. So I've got this cracked beam and I'm going to look at this section right here. I have a width of delta x. If I look at the left side, I have a compressive force in my concrete and a tensile force down in my steel, causing a moment and also have that moment acting at a moment on JD. On the other side, have a compressive force plus change in my compression force, so that my moment is increasing. Tension plus a little bit of change in tension. Causing a moment and a change in moment. My moment changes along the length. So I think moment. I take if I want to find the value of that moment, take the moment about C on the left side. T JD. On the other side, moment plus my change in moment, and C plus my change in T. I put that T plus JD in for that moment, and I'm going to put this in here and multiply it out. these two values go away. And I can say that my change in moment is equal to my change in my tensile stress. And if you recall from structural analysis, your change in shear, or sorry, your change in moment, your shear is equal to your change in moment, or it's the derivative of your shear is the derivative of your moment. So if I solve for delta n, my shear times my shear force times my delta x, and put that in there, I get my shear times the width of my element is equal to my change in my tensile force times the moment. I'm going to stop right there for that one. I know that's really dry stuff. So look at this bottom part of the beam up here at the top of the page. I'm going to look at the shear stress over that element. And the width of delta x, tensile force T on the other side. My beam width, so this, on my left side, I have a T, and on my right side, I have a T plus delta T. So if I want to look at equilibrium, I have to have a delta T change over that width, right? It's called my shear flow. My shear stress now is equal to that delta T, that's my shear flow, happening over this area. Which has the dimensions of my beam width, BW, and the width of my little section that I'm looking at. I just found an equation for that delta T. I can solve it down here. Delta T is equal to my shear force times my width, or my, yeah, the width of my element divided by 30. I'm going to substitute that in. Okay. Delta X will go away. And if I say that that moment on JD is about equal to B, then my shear stress is my shear force divided by my beam width times in the ACI code. We're going to swap out that tau for B. It's the same equation.
Dr. Turner, can you scroll down for just a second?
Down or up?
Down. Thank you.
Mm-hmm. So my shear stress is just my shear force divided by my width of my beam and the depth of my tensile reinforcement is what they assume. And I'm going to also use this equation here on the next. Sorry, I just saw this comment from like half an hour ago about Moore circle. He was wrong. Mostly Moore circle comes into play if you are in geotech. That is the time you will use it the most. If you are not in geotech, doesn't matter. Not doesn't matter, but you might not ever see it again. Except for right now when I'm showing.
For me, your sound is a little muffled. When did you say Moore circle comes into play?
Geotech,
Oh, okay.
yeah. Right, because you're talking about all those little elements in the soil and if they're in compression and whatnot. Yeah. We used it a lot in grad school in my geotech classes. I'm actually, Dr. Manry's teaching mechanics in the spring. I was actually thinking about that the other day, whether or not he's going to include that. So, anyway. So, from structural analysis, my shear is my derivative of my moment, right? And if my moment is my tensile force times JB, then my shear is the derivative of my tensile force times JB. Yeah. If you guys remember Calc 101, if I take the derivative of two things that are multiplied, I get my shear is like, right? The first times the derivative of the second plus the second times the derivative of the first. So the first times the derivative of the second plus the second times the derivative. Pulling that out from 28. So I'm going to look at two different cases. Right, case one is where my moment arm is constant. So if I take the derivative of the constant, it's 0. Right? Derivative of the constant is 0. So my shear is just that constant times the derivative of my tensile force. This is what you would expect from a regular beam, right? Your tensile force is going to vary along the length because your moment varies along the length. And the moment is directly related to that tensile force. So this is called beam action. This is what we're going to focus on. acting like a beam, right? And this means you're, you know, talking for a long time. Your shear flow is that. I'll come back to that in just like this. Your change in your tensile force is just that flow across that horizontal plane that we showed right here. So now what if instead of my moment arm being a constant, right? Tensile force is a constant. So my derivative of that is 0. That means I have no shear flow. Because my steel, this basically means your bottom steel down here is carrying the entire tensile load. It's a single force. It has debonded, everything's cracked, and it's just your steel holding everything together. Unbonded, meaning your concrete and your steel might not be working together anymore. Your shear flow is interrupted by cracks in your concrete. Now your shear force is just this constant times. This is called arch action. It basically means now your beam isn't acting like a beam, it's acting like an arch. What I mean by that is your flow of forces is like there's stuff at the bottom, or I'm sorry, this is the top. Stuff at the top, and then stuff at the bottom, but not a lot happening in the middle. And you basically treat this whole beam as if there's like a part here and a part here and a little bit of a part here, but you don't get to take advantage of any of the concrete between those lines of action. this this occurs in deep beams. I mean, like really deep, right? Deep and short, right? Something like that. Now your forces are more like an arch. Okay. That's the real meat of the mechanics of this. Just trying to show that sometimes the deeper if you have a really deep beam, you're gonna have to design it differently, is basically what that means. You're gonna have to treat it like it's got only parts going on, as opposed to the entire cross section of concrete. So we're gonna design for beam action and not arch action. Arch action is a second semester kind of topic.
It's like a pair of pants.
Right. Yeah. Exactly. Like a pair of suspenders holding up your pants. Okay. Okay, here's our flexural crack at the center. And as you get more towards the outer edges of your beam, you increase your shear force. You're going to increase your shear stress, and you're going to have an inclined crack. So if I have a tensile force, right? Similar to if I have a tensile force here, I added my reinforcement along that line of action, right? If I now have an inclined tensile force, I could put my shear reinforcement at an incline. Not going to, surprise, surprise. But you could. So you could either have, right, here's your crack. You could put inclined reinforcement. Or what we just do in the US is we put it vertically. Right? So we put vertical. Shear reinforcement in the US. And part of that reason is for reversible shears. like seismic, right? You don't just design your building for shear in one direction, design it for shear in the other direction, for seismic things. So I'm going to look at my crack, my shear crack. And let's see, up at the top, I have VCY. I'm going to call that my shear in the compression zone, right? All this is in compression. I have shear acting on this face due to the aggregate in there that wants to stay with its buddy, right? You got aggregate across. Aggregate doesn't want to break apart. So you've got some strength in there or some stresses. If I break that down into its components, I'm going to call this VAY. That's my shear cross crack. Due to aggregate interlock, my aggregate not wanting to break apart or anything. And then I have my shear strength in the longitudinal section. It's just the dowel action, right? It's the, if we're applying a vertical load to that reinforcement, it doesn't want to move, so it's resisting. Notice I have the same thing happening on the other side. Don't have any VCY over here. So if I sum up where I'm going to get shear strength from, I've got right, I've got my shear in the compression zone, my shear due to my aggregate interlock, my shear due to my longitudinal reinforcement, not wanting to move and acting like a bell. So as the shear crack widens, my shear strength due to my aggregate goes to 0. Then a crack forms along the longitudinal reinforcement. So that shear strength goes to 0. And I'm left with only the shear in my compression zone. And putting all of my eggs in one basket isn't so good. All the shear and compressive stresses in the vertical portion at the top. Result in crushing and buckling. So this is assuming that I have no shear reinforcement and a reason to think. Ready to turn the page? Ready. Factors that affect my shear strength of my beam if I don't include reinforcement are the tensile strength of my concrete, and the reinforcement ratio. So what we've talked about so far is the mechanics of why we need reinforcement, right? And how it fails. The big takeaways are shear cracks are going to be inclined because of the change in adding that stress, that shear stress in there. And then incorporating reinforcement to go across those cracks. And I guess the beam action commentary as well. Right? You get deeper and shorter, you're going to act more like an arch than a beam. So that was what all that background was to basically get to. Okay. Now we can actually get into shear design. What just happened here? Oh, did am I missing? Dang it. I knew there had to be more. If I have my, where did they go? Oh, that's cool. Basically, now that you have the shear reinforcement, that's gonna take up your right. That's gonna provide your shear. Strength. I might go back and augment those a little bit better. I'm missing some pages in my notes, but just showing you the shear, the stirrups, or what helps take up that. Now we don't have to rely on the aggregate or the dowel action. All right, if this is our VS is our strength of our steel, our stirrups. VAY is our aggregate, dowel, and then our concrete. Eventually, we just have our shear. Let's see. Yield of our stirrups, and then we have to rely the rest on our concrete. Because eventually we get so cracked that the dowel action and the aggregate go away. So you'll see that in the next, when we start to design, we can only rely on our concrete and our stirrups. So, shear, where does shear? There's one-way shear. Page 401. VN is equal to our phi, and our VN is equal to our shear strength from our concrete and our shear strength from our stirrups. This is on page 401. We're talking about one-way shear strength as opposed to two-way. That's more for a slab, right, within 2 dimensions. On my phi factor, I gotta go to this equation right here. My phi factor is on my phi, which you should have a tab, page 391. Shear is just a flat 0.75. Right, table 21.2. AC is the shear strength of our concrete. CS is the shear strength of our and I said we're gonna focus on one-way shear, which is section. So if we go to 22.5, here we go. We're calculating we're non-pre-stressed numbers, right? How much strength can I count on from my concrete? There's a lot of numbers in here. We're going to get rid of them. But that's a good tab to have. Right? This is page 404. So if this is all based on the criteria of if I meet my minimum shear reinforcement requirement. AB min is your minimum shear reinforcement requirement. I look at this top equation, equation A. You can use either of them. I would recommend remaining with equation A. We're going to focus on it. We're going to focus on, we assume we have enough reinforcement to at least meet minimum. And we're going to use that first equation. That lambda is our modification factor for lightweight concrete. If you have normal concrete, it's 0. I mean 1, not 0, 1. NU is if you have an axial load. If you have an axial load, you get to have more concrete strength. AG is your gross cross-sectional area. BW is your beam width, D is your depth to your neutral axis, depth to neutral axis. Depth to your centroid of your longitudinal reinforcement. F prime C is what we used before. Remember, F prime C is in PSI and comes out in PSI. Note down at the bottom, NU is positive for compression and negative for tension, which makes sense. If you have a tensile load, it's probably going to decrease how much you can apply to in shear. And your shear is not less than 0. If you have more than your minimum, normal weight concrete, so your lambda is 1, and you have no axial load, your shear strength of your concrete is 2 square root of times C. That equation simplifies if you don't account for, if you don't have any axial load. And if you have compressive, it's conservative to take to 0. If you have tension, you should probably account for it because it'll reduce your capacity. If you go to the next page on your ACI manual, there's some other notes. You can't have more than 5 lambda for your FMC. And there's a limit on how much your that contribution from your compressive load can be. We've got a BC max 5. This ratio can only be 5% of your compressor. And also, we go back to 25.3, that square root can't be greater than 100 psi. But that means you have 10,000 psi concrete, which is not likely. But just in case you do, don't account for it, right? What are my minimum shear? My reinforcement minimums are all in the same spot. If we see a little tab for AFmin, AVmin is just on the next page, page 136. All right, there's mine. All right, 9.6 is my reinforcement. We've already done the flexural reinforcement. All right, 3 square root F times C over Fy, or 200 over Fy. And we scroll down, and there's my minimum shear. So it's just on the next page. If you read it, go back. Minimum shear shall be provided in all regions where your required strength is greater than P lambda F times C dWd. This is half of your VC. Right. Great. If I have normal weight concrete, I'm going to divide that all by phi. So VU over phi greater than 1 times square root F times C dW. Two slides ago, I said that VC, if I have normal weight concrete and no axial force, axial load, VC is 2 square root F prime C dWd. So I need to have 80 min anytime VU over C is greater than half of my concrete strength. I mean, there might be areas where you don't need shear reinforcement. That's where our shear diagrams are going to come into play from structural analysis. If I look at there's cases where I'm not required at all. And then these are really small. This is the joist, and then table 9.6.3.4 on page 138. Has what AD means. And obviously we're in non-pre-stress. remember where F times C goes in as PSI and comes out as PSI. So this 50 is also.
Hey, the test next Thursday, that stops with flexure, right? This stuff won't be on it.
Yeah, this won't be on it.
Okay.
I swear, I feel like I'm throwing a lot of stuff at you this year, but it really boils down to something really simple. But it's like, here's all the background behind it.
Yeah, once we see an example, it'll probably make more sense.
Yeah, it's basically like, and even my husband and I were talking about this earlier. I was like, oh, I have to go teach shear. He's like, oh, we try not to rely on shear strength at all. We try to make it all in the concrete. So size your beams accordingly.
So you're saying this is all useless anyways?
No, because you have to know what your minimum is. But because you have to provide the minimum, but generally, but the shear from the stirrups is try not to rely on that. But we haven't put that in yet. Right? That's our VS. We're at DC right now. So let's look at some shear design with increasing VU, right? Increasing nominal, like required, right? As I increase how much I need. This is an important table. This kind of summarizes it. If I have 0, if I don't need any shear strength, if my VU is 0, up until if my VN is 1 times the square root F prime C BWD, then I don't need any shear reinforcement. That's what that AV min just told me. In regions, I have to provide AV min where I'm over 1 times the square root BWD. If I'm over half of my shear strength of my concrete. From half of my shear strength of my concrete to 2, right? You can kind of make a little, this right here. This right here is half of my shear strength of my concrete. This is half the shear strength of my concrete to all the shear strength of my concrete. If I have half of it to all of it, I need to provide AV min but my concrete provides all of the shear resistance. What we were saying is this is kind of where you want to live generally. It's just providing the minimum. But we're not going to do that in this class. Why not? If I need more than 2 square root of times C CWD, right? That's more than my concrete can provide. Now I need shear reinforcement. And I can go back to that equation, right? CVN equals a VU, right? CVN VC plus VS. Solve for VS, and I need my shear reinforcement to provide I need enough shear reinforcement to provide capacity for ultimate shear minus how much I'm getting. My nominal shear, U over C is my nominal. Subtracting out how much I can count on from my concrete. So up until half my shear capacity of my concrete, I don't need any reinforcement. From half to all of my concrete reinforcement capacity, I need to provide at least AV min. If I have more, if I require more capacity than my concrete can provide, I have to make up for it with shear reinforcement, my stirrups. And just remember, this was all assuming that I have no axial load and normal weight concrete. And my kid is home from school. We're about to get, we almost had an Elsa come down to me. They all dressed up for school today. Let's see. So how do I calculate my shear reinforcement capacity? My shear capacity for my reinforcement is my area of steel and shear times yield stress of that reinforcement times D divided by spacing. Maybe we should stop right here. I know I'm throwing a lot of you guys. Because now we're going to talk about designing the reinforcement. So let's stop right there. We'll pick back up here next week. This will not be on the exam. But the big takeaways, like I said, were what does a shear crack look like? How do the dimensions of my beam affect whether or not I use beam action versus arch action? When do I need AV min versus not, versus when I have to add in some reinforcement? Is what it all kind of boils down to. I know that was a lot of information. If you go back and have any questions, please send me an email or something. Does anybody have any questions so far? Are y'all just brain dead from this?
Definitely brain dead.
Yeah, sorry, we're just pounding through shear. So
I was trying to tag my book when you were going through all those tables, and I don't think I got them all, so I'm gonna have to go back and at least watch that.
yeah, and I try to make a point of when I have stuff of putting the page number. But so yeah, all the mechanics stuff was just understanding why we need it and what happens if we don't, basically. So, and then just deriving things, because I like to derive things. I know you guys would sometimes rather just the equation, but it's nice to understand where things come from. So if that is all, I can let y'all go. I'm gonna stick on with Justin and go over more circles. But y'all can go.
My brain hurts. A good idea or not?
I know, that's why I was like, if it doesn't work out today, if your brain is like done. But, I don't know. Anyway.
Well, I'll let you teach it to Justin, and then I'll get Justin to teach it to me. How about that?
You might stick around so you can teach it to me.
I was about to say, I was like, I'll talk about it with anybody who wants to stay out. We're not going to talk about anything secret. So,
I think my questions are just pretty straightforward.
yeah, it's funny because I like how you're like, I have a 5 to 10 minute question. I'm like, more circle is not a 5 to 10 minute discussion. But yeah.
I'm trying to remember what it was.